Here is a breakup of module 2 of your syllabus. The title of the module is Discrete Fourier Transform. The important things we are going to cover in this module is frequency domain sampling and reconstruction of a discrete time signal, the discrete Fourier transform, DFT as a linear transformation, properties of the DFT like periodicity, linearity, symmetry, multiplication of two DFTs, circular convolutions, and a few more additional properties. The very first topic in your syllabus we see is frequency domain sampling and reconstruction of discrete time signals. Now, before we get to what is frequency domain sampling and reconstruction, before we talk about sampling in the frequency domain, I think it's good to have a look at what happens in the time domain. Now, what do you mean by sampling? Sampling is a process of converting a continuous time signal into a discrete time signal. In other words, an information which is present at all times we are going to consider at only particular discrete instance of time. To assist in this particular process, we have something called as the sampling theorem. Now, the statement of sampling theorem in the time domain goes something like this. A continuous time signal can be represented in its samples and can be recovered back when sampling frequency Fs is chosen to be greater than or equal to the twice the highest frequency component in the message signal. If the message signal has the highest frequency component denoted by Fm, then the sampling frequency Fs should be twice or more than that particular value. This is the basic condition so that once you sample the signal, it is possible to get back the original continuous version of the signal. The important term here is to be able to reconstruct the signal back. Just to illustrate the process, we have drawn a red line which represents a continuous time signal. The notation for a continuous time signal is x of t and the horizontal axis being time. So x is a function of time which is continuous. Now, you can observe here we have illustrated some dots. These dots represents the samples or the instance at which we are capturing the information. We can observe that these values are uniformly spaced. So this is said to be uniformly sampled, where we decide on a particular interval for obtaining the sample. This quantity, which is called as capital T or Ts, for example, is called as the sampling interval. Now, in this diagram, we can see that the value is recorded at integer multiples of this particular t. So, if the first value is at 0 into t, the next value is at 1 into t and 2 into t and so on. So, these values which are indicated will serve as an index. So the index we have is 0, 1, 2, 3, 4 and so on. When multiplied with the value of t or ts, it gives you the particular instant of time. Now this time is proportional to the frequency. So t is equal to 1 by fs, where fs is called as the sampling rate or it's a sampling frequency. Now, as we have already understood, suppose we have an application which has a maximum frequency component which is 4000 Hertz, then in order to reconstruct, the minimum condition is given by Nyquist rate, which happens to be equal to 2 times of the maximum frequency. So twice of 4000 will be 8000. It doesn't mean that you cannot go more than that. So if you do above Nyquist rate, it is called as oversampling. So if you're doing double of that, say 16,000 Hertz is the value of Fs, then it's called as oversampling. So will be any number like 32,000, 64,000, 128,000 and so on. But if you get a number which is less than twice, for example, Fs value, if it is 6,000 Hertz for an application with the maximum frequency 4,000 Hertz, then it is termed as undersampling. Therefore, we have three cases: exact sampling, where you go with Nyquist rate; oversampling, where you're exceeding Nyquist rate; and undersampling, where you're doing less than the Nyquist rate. This same phenomena can be shown in the frequency domain as well. In this frequency domain, we plot the spectrum. The horizontal axis is a frequency. The vertical axis indicates the quantity which is in the frequency domain. So you can see it's a function of omega, where omega is a frequency. Now in the diagram here, we can clearly see the three different cases that were discussed. First one is said to be oversampling, where Fs value is greater than 2 times of Fm. Now we observe that the information is represented by the spectrum. So you can see the center frequency for the first term is 0, and on either side we have copies of the same information, or the spectrum is illustrated to be symmetric. Now, as a part of sampling, we are obtaining replicas of the spectrum. So you can see that the same information which is found at the center is repeated at frequencies illustrated as omega s, 2 omega s, and so on. The separation between the original and the replica here is equal to omega s. In other words, the sampling frequency omega s, which is derived from f of s, is going to decide the separation. So greater the value of fs, more distant will be the replicas. So we know the spacing from here to here, it's omega s, and from here to here it is also omega s. So if fs is more, the separation will be more. Now what is the advantage of this? The advantage of this is that, as we are aware, the information which are the replicas, or what we call as the harmonics, they are duplicates of the original, so we can discard it. It's sufficient to take the spectrum which is at a center frequency which is 0. Now to extract it, we may use a device which is called as a filter. Now a very simple filter will help you to extract the center frequency at 0. So this process is very simple when we go for oversampling. Now let us talk about the second scenario. When the fs value is equal to 2 times of fm, we can see that the separation between the original and replica is minimal. That means that you can see it is attached to the original component. So the original and its replica are just beside each other. Now in this scenario, as we have understood, fs value is less, hence the separation is also less. We call it as exact or properly sampled. Now if you try to extract only the original component using a filter, the filter here has a very stiff requirement. It should be like an ideal filter. So we know the response for an ideal low pass filter, it is almost vertical, and getting a response like this is highly impractical. A practical filter would actually have a more tapered response, so it is going to reduce slowly rather than fall suddenly, and this will cause some of the unwanted components to leak. So you can see the shaded region here. Along with the main spectrum, we'll also get the unwanted replica also, which we cannot distinguish is information or it is not information. Therefore, here we are inviting the unwanted signals. There is a leakage in the spectrum. So this is the reason that you cannot properly recognize the signal. Next, coming to the undersampling case where fs value is less than 2 times of fm, here we can clearly see the spacing is even more less to the extent that you have overlapping. And this overlapping in terms of frequency is called as aliasing. So when a high frequency component is occupying the position of a low frequency component, that is termed as aliasing, and wherever the signal overlaps, we know it may result in anything. The signal may add, the signal may subtract, the signal may cancel each other, anything may happen, or in short, we say the signal is distorted. So the information in the overlapping region is said to be lost. So recovery in the case of undersampling is highly impossible. So these are the 3 cases. Here we have spoken about the sampling in the time domain. Now coming to the frequency domain sampling. We begin by considering an aperiodic finite energy signals. Now why aperiodic finite energy signals? In nature, rarely we encounter periodic signals. Information in general is available at a particular instant of time and then it changes. It doesn't repeat. So this is probably the more common type of signals that we encounter. So an aperiodic signal which has finite energy, when you transform it to the frequency domain, it will have a continuous spectra. It will have a continuous spectrum. Now, the method of changing it to the frequency domain is by applying what is called as Fourier transform. So since we are talking about a discrete time signal, here we are talking about the discrete time Fourier transform or DTFT. Therefore, the DTFT of an aperiodic finite energy signal is given below. The sequence is said to be x of n. X of n is multiplied by a complex exponent e power of minus j omega n, where omega represents the angular frequency. We take all the terms in x of n and multiply it with the respective exponent, and the summation of that is called as capital X of omega. Capital X indicates the transform. Omega says it's a function of frequency. Now the problem with this spectrum is that it is continuous. If the signal is continuous, then we have too many points to store and process. So it becomes very challenging as far as computation is concerned. Therefore, we say that x of omega is not a computationally convenient representation of the signal x of n. Now, x of omega is periodic and it has a period which is equal to 2 pi. And only samples which lie in the fundamental frequency range, they are taken, and suppose we sample it periodically. So it is sufficient to consider the frequency from 0 to 2 pi. Please note the horizontal axis omega, and the signal is now called as x of omega. So this is the continuous spectrum, and the solution to reduce the number of points is to go for sampling. Now how do you sample it? We decide a spacing which is given as delta omega, which is 2 pi by n. So the total duration in frequency from 0 to 2 pi, the total interval from 0 to 2 pi is divided into n parts. Therefore, each part will be 2 pi by capital N. Therefore, in the original equation called as equation 1, we shall replace the value of omega, which is equal to 2 pi k by n, where k is the integer multiplier. So we know the separation between any two samples is delta omega, which is equal to 2 pi by n. To yield the frequency at that point, we have to multiply by the index. When you multiply with 0, we get the answer as 0. When you multiply with 1, you get it as 2 pi by n. Next will be 2 pi by n into 2 into 3 and so on till the very last point, which is called as k. So the k is the one, the very last point value in k is going to be n minus 1. So this yields a total number of points between 0 to n minus 1 is going to be capital N. So inserting this value of omega in equation 1 will give you the form like this. So we can see that omega is now changed to 2 pi by n into k, and similarly here in the exponent also omega is replaced with 2 pi k by n. Now this summation 2, where k value is between 0 to n minus 1, has infinite number of terms, and any thing which is infinity can be divided into many number of finite parts. How many? Precisely infinite. Okay, so here we are going to subdivide it into infinite number of summations where each sum contains capital N terms. To describe this, you can see the process here. On the RHS, you can see the limits. The limit starts from minus n to minus 1. It is n terms. The limits are 0 to n minus 1. This also has n terms. N to 2n minus 1, it also has n terms. Like this, it can go on. That's why we put dots on either sides, because the number of terms we can have like this is infinite. To represent the above in a more concise way, let us do some replacement. We can write the above equation in a more general way by using two summations. The outer summation is controlled by a variable which is called as L, where L is an integer. It can have a potential value from minus infinity to plus infinity. The inner summation is having the limit n is equal to ln to ln plus n minus 1. Suppose we insert the value of L is equal to 0, what happens? The lower limit, it becomes 0 when you put L0 because n is equal to ln, and the upper limit n is equal to ln plus n minus 1 on substituting L is equal to 0 gives you n minus 1. So we observe that we got one term whose limit is from 0 to n minus 1. In such a way, when you put different values of L, suppose we put plus 1, we get a particular range. When you put minus 1, we get another range. So this summation describes each and every term in the summation we showed above. Next, to do further simplification, let us change the index in the inner summation from n to n minus ln, and also will interchange the order of summation. Therefore, the above equation now changes. So the inner summation after changing n to n minus ln will now become n is equal to 0 to n minus 1, and we brought it outside, and the summation which is outside will now go inside. So we have L is equal to minus infinity to plus infinity x of n minus ln. The exponent also, you can see that the value n is changed to n minus ln. We can notice that the quantity here we have highlighted, or we have put a bracket. Okay, we will denote what this quantity is just in a while. And here also, please remember the value of k is going to be between 0 to n minus 1 always. Now, if we pay attention to the last exponent, that exponent could be simplified. So we know that the exponent is having a power which is a sum of two terms. We can actually split it into two exponents. So using the properties of exponents, we can have the first term indicated here into the second term. The first term we can keep as it is. The second term, if I consider you observe that n is common in both numerator and denominator, hence it cancels. And what is left is e power of j2 pi kl. K is an integer, L is an integer. So we are talking about integer multiple of 2 pi. So whenever you have an integer multiple of 2 pi, the answer is equal to 1. This answer could be easily shown like this. For example, you know Euler's relation, e power of j theta is equal to cos theta plus j sin theta. Suppose we consider both k and L to be 1, which are integers. You end up with e power of j2 pi. The answer of that would be cos 2 pi plus j sin 2 pi. Okay. Now we know that cos 2 pi answer is 1 and the second term is going to be 0. And this proves what we have done here is correct. Okay. So 1 plus 0, the sum is equal to 1. Now inserting these values in the previous equation 2, we can observe that the exponent here simplifies, and this is what we get. Now the quantity inside the bracket can be given in name. We call it as xp of n. Now this formula here says that xp of n is a summation of the term x of n minus ln. So n minus ln indicates a shifted version of x of n. So we are considering many shifted versions of the signal x of n, adding it up together, and that signal is called as xp of n. So therefore, the equation 4 describing xp of n is obtained by the periodic repetition of x of n every capital N samples. So the repetition interval we have is capital N, or in other words, it is periodic with a fundamental period which is equal to capital N. Now since it is periodic signal, we can apply what is called as a Fourier series. Initially we took the Fourier transform, it was for a periodic signal. Now we are going to expand xp of n taking the help of Fourier series as follows. So xp of n is written as summation k from 0 to n minus 1 ck, which is called as the Fourier coefficient, e power of j2 pi by n kn. So this equation 5 is the representation of xp of n taking the help of Fourier series. In this equation, we know the n value is going to be between 0 to n minus 1. The Fourier coefficient is described as ck is equal to 1 by n times summation n between 0 to n minus 1. Please note here the index is k, here the index is n. The input here is called as xp of n multiplied with the exponent e power of minus j2 pi kn by n. So here we had plus, here we have minus. And the value of k for ck, k is between 0 to n minus 1. Now, a comparison of equation 3 and equation 6 tells us that the equation 6 ck is nothing but 1 by n times the equation 3. So in equation 3, if you compare, you'll find a similar summation or similar looking summation. Therefore, we establish the relation between the two as ck is equal to 1 by n times x of 2 pi k by n, which represents samples of the spectrum. Therefore, substituting this equation 7 in equation 5 will give you xp of n. So we are substituting for ck now. xp of n is equal to 1 by n times summation k from 0 to n minus 1 x of 2 pi k by n into e power of j2 pi kn by n. So this relation proves something. It proves that on the RHS, the input is samples of the spectrum. X of omega was a spectrum. We have sampled it. Now from the samples of the spectrum, it is possible to obtain the value of xp of n, which is a periodic repetition of x of n. Therefore, equation 8 provides the reconstruction of the periodic signal xp of n from the samples of the spectrum x of omega. But there still remains something to be proved, that is it possible to get x of n? The recovery of x of omega or x of n from the samples of the spectrum, there are some conditions to be satisfied. What are these conditions? As we are aware, xp of n is the periodic extension of x of n. Therefore, x of n can be recovered from xp of n if there is no aliasing in the time domain. That is, if x of n is time limited to less than the period capital N of xp of n. So since we have replicas inside xp of n, provided there is no overlapping between the replicas, you can recover it. This fact is shown in the example below. So let us consider that our information x of n has L points. So let us take some data at these L points. For simplicity, let's say L value is 5. So 5 points, there are 5 data assumed. In the first picture, we are showing that the repetition interval to get xp of n from x of n is said to be capital N. Now, if n value is, let us say, equal to 5, we observe that we can see the original information at the center, and on either sides we can see copies of those. Now, is it possible to get back the original? Yes. We just have to count the number of points which is equal to L and we get the information. That's not a problem. But when you say that the n value is less than L, in this case, let's say n is 3. So the first 3 points are shown, 3, 2, 1 are the values, but the remaining points, they vanish because once again we start repeating and the information which is there has been overwritten. This is called as aliasing. So the condition, that is n value less than L, will result in aliasing, and you cannot get x of n from xp of n. But if you prevent aliasing by keeping n to be greater than or equal to L, then there is no aliasing, and from xp of n you can capture what is x of n. So this is the information and this is the condition that has to be satisfied. So finally, x of n is non-zero in the interval, which is the points between 0 to L minus 1, when the condition, that is xp of n is equal to x of n in the interval 0 to n minus 1, when the value of n is greater than or equal to L. But when n is less than L, we cannot recover it because there is time domain aliasing. Thank you all.